Let's talk about differentials, but first some notation. So I've got delta y. Delta y is the actual change in the y direction based on the function's graph f of x, as opposed to dy over dx. If I do a little bit of algebra here, I can write that dy is equal to, I'm just going to cross multiply, f prime at that point of tangent CA dx. This differential here, dy, is the difference based on the tangent line. So this one is an approximation. We're going to use the tangent line and its difference in the y direction to approximate the actual difference in the y direction. So this is the basis for what we're doing, and we're going to be using this formula, which is based on that tangent line. I'm going to start off with a really simple, straightforward example, and then we're going to jump into differentials to calculate the difference in a surface area and a volume of a sphere. Let's go ahead and start with this one. So we want to use differentials and the linear approximation, which means that we are using this tangent line formula to estimate delta y for y is equal to cosine x at pi sixths, and we are given a dx. So we know that the actual difference in the y direction can be approximated by dy. Using that formula up above, we've got dy is equal to the derivative at a is equal to pi sixths, times the difference in the x direction dx, and that's going to be our 0.014. So the only piece I don't have is my derivative. Let's go ahead and figure out what that derivative is. So f prime of x is the derivative of cosine. That's going to be a negative sine x. So f prime of pi sixths is equal to negative sine of pi sixths. Negative sine of pi sixths is equal to negative sine of pi sixths. That's going to be opposite of that 30-degree angle, and that's going to be a 1/2. So as I put everything together then, dy, which is approximating delta y, the actual difference, is going to be the derivative at pi sixths, that's negative 1/2, times the difference in the x direction, which we were given as 0.14. If I go ahead and do that calculation, I end up with negative 0.007, and this is my approximation for dy. Let's do an application next. This is a great application of the differential using an error in the x direction or the input. So we can only measure the radius accurate to 0.5 centimeters, and that's going to give me a differential or an error in the y direction. So for part A, we want to estimate the maximum error in the volume. So I've got my volume here, and the volume is that 4/3 pi r cubed. I know that I want to come up with the maximum error. This is going to be the differential in v, and we're going to approximate that with dv. Well, my variable here is r, so if I were to take a derivative, I would have a dv dr is equal to v prime of r. So I can go ahead and just rewrite that differential formula as dv is equal to, I'm cross multiplying now, v prime r dr. Okay, so what do I need and what do I have? I have dr, that is 0.5 centimeters, but I don't have v prime of r, and I actually need v prime of 25 centimeters. So let's go ahead and do v prime first. So when I take the derivative, so v prime is equal to, taking the derivative of my formula here, 4/3 pi times, I'm going to do the power rule on r cubed, that's going to be 3r squared, and this is v prime, and I want v prime at 25. I can cancel my 3's, and I have 4 pi times 25 squared. I can come up with an approximation of this, or I can use an exact value. If I multiply 4 times 125, that's 100, times another 25 is 2500, so I have 2500 pi. If I put that, though, into my calculator, I've got 2500 times pi. And that gives me 7,853.9. Let's round that to 7,854. So about 7,854. Putting this into our differential formula, I'm going to switch colors here. So I know that the actual change or the actual error in the volume can be approximated by dV, which is equal to V prime of our R, which is 25. Everything's in centimeters, so I'm not worried about my units. dr. Putting in the values that I know, I've got dV is equal to V prime of 25 are these two values. I'm going to start with the 2500 pi. We'll do an exact value first, times dr. dr is our 0.5 centimeters. If I go ahead and multiply that through, 0.5 is really just 1/2, so that's going to be 1250 pi. This is a difference in the volume, so I've got cubic centimeters. And if I put this into my calculator, I end up with 3,926.99. Let's call that about 3,927. So this is going to be 3,927 cubic centimeters. Not a small difference, right? So this would be the maximum error or differential in the volume. Let's go ahead and do the same thing for the surface area. So as I'm putting the surface area formula together, I know that if I take a derivative a prime, that's going to be equal to dA over r as my variable, dr. So rewriting this by cross multiplying and isolating the dA, I've got dA is equal to a prime of r, I'm going to put 25 in here, times dr. And we know that that dr is that 0.5 that we had up above. Okay, so that means that what I need to figure out here is a prime. So if I'm looking for a prime of r is equal to the derivative of my area formula. So that's going to be 4 pi times r squared. That's going to be as a derivative to r. So I end up with 8 pi r. If I evaluate this at 25, I have 8 pi times 25, which is equal to 200 pi. I can also put this one into my calculator to get an approximation. So 200 times pi. And that would be about 628.3. Now I'm not going to round at this point until I'm done. I don't want to round when I'm looking for an error, right? I don't want to introduce an additional error. So let's jump right back into that differential. So dA, which I'm using to approximate the actual difference in the surface area, is going to be equal to a prime of 25, that's 200 pi, and dr, so times dr, that's going to be 0.5. Again, everything's in centimeters, so we're good here. And I end up with 100 pi. 100 pi, or if I multiply that out, I get 314.2. This is an area, so 314.2 square centimeters. Again, not a small difference. Make sure you watch this next video. It's on linear approximations and usually shows up in the same section that differentials do. Thanks so much for watching.